Thank you, Alan, for the invitation. I really hope that the boring part is over now. Not a big promise, but still I will try. So I'm here talking about a real use case scenario where we have applied some explainable AI technique in a specific context that is a predictive maintenance, okay? That we are used in Metro do Porto real-world data. So this is, of course, a teamwork of many people from University of Porto and INESC, and it was also developed within this XPM project that just finished last month. So Helen has made a lot of the background motivation, but regarding this predictive maintenance specific domain, there is this specific need for explainability, but for a specific type and type of users, okay? So basically what we know so far is that black box models are quite effective at a lot of tasks, right? They are also good whenever we are trying to catch anomalies within a functioning of a machine. They are accurate, okay? But the thing is, do you think that if you say some maintenance team that let's take the case of the railway or vehicles of Metro do Porto, if you say someone, your train is about to fail, please remove them from the operation and check what's happened. If you don't say anything else, do you really think that they will do that? They will not. And also it happens in industry-wise. So this, to become effective, it really needs this explanation layer so that we can kind of support what is the black box model would say. And that is not only for short term. In the morning, I was listening to a talk on sustainability in AI. And one of the things that is nowadays a critical issue is to explore and maximize the useful life of an equipment. We just want to take out of the equipment all the time that we have, so that we cannot just replace them in preventive maintenance actions like we do in our cars, just because it might break down, okay? So we are trying to give some expertise so that better maintenance plans are designed, and hopefully in the future, better design of the equipment. So our overall goal is, of course, to identify these faults so that we would not stop the equipment from functioning, but also to have at the same time and online a kind of support explanations for those anomalies. So what I'm showing here is our latest work that is an online anomaly detection with explanation, okay? We have basically 2 layers, and I'm going to detail them next. So we start with the basic one, let's say, that come from a machine, okay? And we do want to trigger an alarm whenever there is something wrong, something that is an anomaly, okay? So that we do decide if we should trigger an alarm or not. So basically, this is the way we trigger alarms. A more detailed thing is that whenever we are in an online setting, we should account if the failure, and whenever it's an operating condition of an asset, if the fail was a persistent fail or the equipment was able to recover. Because if you know, for instance, in a train door, if we are accounting for the movements of the open and closing cycles, if you put your hand on the door would not close normally. So that would be an abnormal movement, but it's not a fault, right? So in order to account for those type of things, I will not enter the details here because our goal here is on explainability, but we do pass these fault predictions through a low-pass filter so that we only trigger an alarm whenever subsequent signals of alarm are persisting, okay? So now what? We need, at some point, whenever we trigger an alarm, to have some explainability associated to that. So what we do is to add a new layer, which we call the anomaly explanation layer. Basically, this layer would receive as an input two things. So basically, the original time series, so it's not pointing, so the original set of multivariate time series, and as the target, we use the reconstruction error, okay? And we build a model that maps this input series to this reconstruction error. And why? Because we want a rule system that is able to explain reconstruction error, because that is an indication of a failure. And moreover, we want this rule system to be specifically accurate at very high reconstruction errors. Why? Because that is an explanation for a potential anomaly. So that's why we give some sampling here. And I just basically here have what we are currently using. So first of all, we are using an online rule learning algorithm for regression, which is AMRules. And in order to deal with this imbalanced, we try to make the rule system to focus on the extremely high reconstruction errors, okay? And for that, we do need some data level strategy, as it happens on classification, imbalance classification, when you can do a lot of data level strategies. Here in regression, we kind of do the same. And we had two proposals. Basically, we have one undersampling technique and one oversampling technique that tells you about if an incoming example is a reconstruction error that is very nearby the average value, so probably you should not incorporate it into the rule learning system. And on the other hand, if it's too far from the median, maybe you should oversample, okay? So we have a kind of heuristics for choosing whether the incoming example should be included in the new rule learning model. So once that it's done, we get a set of rules, okay? We can have two types of explanations with these rules. We can have either global explanations, which basically look at all systems during the operation context, or we can look at them example by example. And if whenever an alarm is triggered, we look at the rules that are activated at that time, we might have local explanations for that specific failure, okay? That was our intuition. So now let's see how this works within this specific context of Metro do Porto. So basically, they gave us access to the data, and they told us about a problem that they have, which really affects them, which is this APU system, which has no redundancy, as far as they told us. And it's basically the unit that is in charge of maintaining the vehicle aligned with the platform. So it's a highly requested equipment. It means that whenever it stops at a train station, people are moving out and moving in, and he has always to be injecting the right amount of air so that the vehicle keeps aligned. Whenever that breaks down, the train has to be stopped, people have to move out the train and have to be in another train, okay? And that for them is a really huge problem, and they would like to know beforehand if that APU system is about to have a failure. Okay, so basically this was our setting. A mechanical engineer decided on which sensors he could use for measuring signals on this APU system. And he decided to install 16 sensors on these 4 modules. Okay, don't ask me about the details regarding mechanical engineer. I'm not very expert. But he decided that this would be the critical thing. And we had data with 1 Hz sampling frequency, which we received in our server every 5 minutes. And we had access for this specific study of 3 months of data. Of course, in these 3 months of data, as you will see, we only have 2 failures, which is kind of poor for us, but from Metro do Porto is kind of big, because people in those 3 months have to move out of the train and go to the next one. But let's see how it goes with this. So basically I have here, by the way, the data set is publicly available, so it's here, okay? We have it on Zenodo. We have 8 analog sensors, okay? And 8 digital sensors. I call attention to this LPS because this is a digital signal that is actioned by the control central system of the vehicle. Whenever that LPS is activated, the driver knows that he has to stop the train, okay? What we want is not to make predictions after this LPS system. We want to be able, by monitoring that specific APU system, be able to trigger an alarm in advance. And how much time in advance? Well, Metro do Porto told us that, okay, for this to be useful, really useful, it has to be 2 hours before, so that we don't put the train in operation for the next trip. So the idea was to be able to spot these failures at least 2 hours before. And these were the failures that were supplied to us by the maintenance report. As you see, very small failures, very small number of failures. But look, we have one that is of a type hair leak and another that is a type of oil leak. This one was running for a few days. Why? Because the system was able to recover. It was on stress, but, well, from 11 to the 14th, it was able to still cope with it. And this one, well, this one was pretty fast, right? So these are also 2 types of failures. Just to give you, I will give you the first preliminary results that we have, but to be clear, what do we consider a true positive, a false positive, and so forth? So basically, whenever we have an alarm that is within overlapping the true failure period, we say that we have a true positive. Okay, and details are that if they are less than 1 day apart, they are considered the main ones. Of course, we have false positives if we have no failure. And regarding early detection, we only account for early detection if this comes before this LPS signal. Okay. So our experimental setting was this. So we opt for 30 minutes data chunks, and we took 1 month for training and 2 months for testing. So we are doing a sequential evaluation. This is online streaming scenario, okay? And for the anomaly detection, we use autoencoders. Of course, one of them was better than the other, but this is all about the architecture of the autoencoder. What I really want to show you is that, okay, we have these 2 failures are here marked in gray. Okay, this is the air leak and this is the oil leak, the one that took longer. And if we look at the air leak, we got different results according to different autoencoders. we signal an alarm, basically when we go above this 0.5 threshold. And basically with an LSTM autoencoder, we are able to detect the two failures, but not so much time in advance, right? The first one, even this one, it wasn't able at all to spot before the LPS signal. So basically this vertical dashed line here is the LPS system. So at this point, the driver knew that he had to stop the train. Then we tried other ones, and we see, for instance, this one, which is, well, it detects very early, but also it does a lot of false alarms here. So this is also a problem for this explainable predictive maintenance. We do not want a model that is trigger an alarm very often, right? It will lose the reliability. And finally, this was our best approach, which basically was able to detect more than 2 hours before, okay, the LPS. It did not give the false alarm, and it was good. Okay, you can say, what about this? Because this is only one failure, and this was particularly good at this failure, not so much good at the other, but still it's a principle. The thing is, we want to look at the rules that were triggered by this best anomaly detector. And if we look, for the first failure, we got very small and compact number of rules. We get these kind of rules. So basically what we want is rules that are very good at high stream values, okay? But we don't care about the prediction of the rule. We are interested in the left-hand side of the rule, right? What are the conditions that lead to the high reconstruction error? And basically what we achieve here is something that the maintenance team might, I'm saying might because we didn't check with them, might understand, right? So basically, at the moment of the hair leak, our rule learning system triggered these 3 rules. Of course, they start at different times, they are active for different times, but still, during the failure, those were the rules that were triggered. Regarding the oil leak, which is the other fault, we also got a quite small and set of rules, okay? This time was four rules, and again, this might be interpretable for the maintenance team. So basically, regarding our case study in Metro do Porto, we were able to achieve a kind of good performance using a specific autoencoder. We did get a set of rules that are quite compact, and they seem aligned with the problem, because the mechanical engineer that was working with us, he said, okay, the sensors that are indicated are related, makes sense that they are related to the air leak. Of course, that we didn't check with the maintenance team, and we didn't even know if it's enough, of course. Much more work would be necessary, and also much more data, right? We have to tell them. And again, the overall message is that we propose this 2-layer architecture. So we need the deep learning, we need the black boxes to spot these anomalies, because we know that they are good. But we, at the same time, we need some explainability. And one way of achieving explainability is through a rule learning system. So that's our methodology that we applied here, but it doesn't mean that it's specific for this case study. So basically, this was where we have applied these layers in real-world data, okay? So I here made available some of our references, and I'm happy to answer any of your questions. Thank you.
They should be on. So, questions? Come on, we had one rule. One rule. Oh, thank you very much.
Thank you. Decision things. Is that the final solution, or did you select on one of the models?
I don't understand. In space shuttles?
Yeah, in spaceflight, they had this redundant computation, and systems would vote if they would raise an alarm or not.
I did not knew about that. So
No, I just saw the three models, and they were slightly better and worse at being hysterical or detecting early. So it could be that if you team them up.
Team them, I understood. Okay, nice suggestion. Yeah, maybe an ensemble. Yeah.
Any other questions? Oh, yep. Oh, sorry. No.
Thanks, Prof. Ribeiro, for your presentation. Just a quick technical questions. The input shape is a set of time series, right?
Yeah. It is a set of, it's like this.
Of 1 second each.
1 second each, yeah. And we have 16 of them.
Of different sensor-based data.
Yeah, 16 sensors.
And did you use I know it's a tricky question, did you use a test set to validate the trained autoencoder?
No, the thing is that we train on the first month, okay? And then we capture the following observation, and we incorporate that in the autoencoder, and we predict, and we do kind of sequential, okay? We predict, and we retrain again. So basically it's an online learning, because the idea was to be able to spot this during the operational context. So it has to be while the train was in operation.
And you got the perfect reconstruction error, right? Almost perfect.
The perfect, what do you mean by the perfect? Well, basically, most of the things are very low. The reconstruction error is very low because the train kind of functions. But sometimes it goes very high. And what we did for a first approach was to establish that if you go above that outlier definition of extreme outlier by the box plot, if the reconstruction error goes very high, we would say, well, this might be a failure. And what we do for having subsequent failures is basically to these 1 or 0 signals, we apply a low-pass filter. So basically, we smooth the signal. If we have too many ones indicating that is a failure, then the low-pass filter will signal that. Otherwise, if the equipment was able to recover, it was a one isolated thing, then it will continue below 0.5. Again, 0.5 is an ad hoc threshold. Of course, you could tune that. Okay?
Okay, thanks. Just last question. Have you thought to convert this problem into not a recurrent neural network, recurrent autoencoder, but more as a convolutional autoencoder without using time resolution?
We have actually tried, this one that we have a convolution here is also temporal convolution. But regarding autoencoders, the ones that gave us the best results so far was this one. Of course, we also are thinking about transformers and other kind of models, but the ones that take into account the time so far were the best that gave us the result, of course, on this data set.
Thank you.
Okay.
Okay, one last question.
So if I understand correctly, the target of your rule learning system is a reconstruction error, right?
Yeah.
So does it mean that it's kind of similar to tree-based models where the more important rules would have more importance in the regression parts?
Yeah.
And you said that you want a rule to focus on high reconstruction error.
Mm-hmm.
Did you achieve that with some kind of weighting of certain samples, or was it through some loss function?
It was through data sampling, okay? We have applied two, basically one undersampling and one oversampling. So whenever the rule learning system is receiving one example with a given reconstruction error, looking at the reconstruction error, it decides if it should incorporate that example or not. Okay, so it's a data level.
Okay, let's thank the speaker again.
Okay, thank you.